Okay, so on Monday we had started discussing waves in general, not electromagnetic waves. And we had seen that the important things for us were, we made several definitions like what is the wavelength, the wave number, the frequency, the angular frequency. And we had also seen that for a general wave, we can write it in this form. The wave will have some shape and its position and time dependence will have this general form x minus vt plus hx plus vt. So if something has this form, its position and time dependence has this form, then we call it a wave. And we had a special kind of wave, so-called the harmonic waves, which are nothing but the sines and cosines. And the important property of these sines and cosines is that any wave you can write as a superposition of them. So if you study the properties of the waves, the harmonic waves, in that case we already can determine the properties of a generic wave. And we had also seen that if a function has this form, it satisfies this equation, the second derivative with respect to x is proportional to the second derivative with respect to time, and the proportionality constant gives us the velocity, the speed of the wave. And we had seen one example, the wave on the string. And in that case, we could determine the speed of the waves on the string, and the velocity turned out to be square root of t over mu, mu being the mass density. So this was what we had done. Any questions up to this point? Okay, for a wave, besides the wavelength, angular frequency, amplitude, there is one more property that we would be interested in. If we just consider waves on a string. So I can create a wave just oscillating my hand in the vertical direction, or I can create a wave by oscillating my hand in the horizontal direction. These two waves are different. They are not the same waves. These are what we call the polarization of the wave. That is the direction in which a quantity fluctuates, deviates from the norm. So we have, in fact, two kinds of polarized waves. There is the transverse polarization, transversely polarized wave, in which the disturbance moves in a direction perpendicular to the velocity. So if you consider this one, what is wave? The wave is created by the deviation of the position of the particles making the string from the horizontal. Those deviations can be in the vertical direction, or it can be in the horizontal direction but perpendicular to the string. So both of these polarizations, they are perpendicular to the string, but the wave moves along the string. So there is the propagation direction of the wave, which is given by the velocity of the wave. And then there is the direction of the disturbance, whatever that is. If these two are perpendicular to each other, then we call it a transversely polarized wave. So this is one kind of a wave. Now the second kind of polarization we will be interested, in 3 dimensions, we have 2 different polarizations for a transversely polarized wave. Either, let's say, if the wave is moving in the z direction, it can be polarized in the x or the y direction. So that is what we call the polarization, transversely polarized wave. Or the other kind of polarization we have is the longitudinal polarization. So there is this longitudinal polarization. Now, what we mean by a longitudinal polarization is, for example, sound waves are longitudinally polarized. You cannot create transversely polarized sound wave, but you can only create longitudinally polarized sound wave. And what does it mean to be longitudinally polarized? If you think of what sound wave is, so there's something, that drum, let's say, that vibrates. So it compresses the air nearby. So it's a compression wave. So it compresses the air and then relaxes it, this compression is created by, let's say, the motion of the particles in this direction. And the wave is also moving in the same direction. So that is what we call a compressional wave, a longitudinally polarized wave. That is, whatever is creating this wave, in this case it will be the displacement of the atoms making the air or the medium, they will move in the direction of the velocity of the vector. On this string, well, you cannot create longitudinally polarized wave. Well, of course, you can create still sound waves, but they won't be waves in this sense. But if you take a slinky, I forgot to bring one. Do you know what slinky is? It's just this long spring. You can buy it from kids' toy shops. Yeah, they're. It's just toys for. I mean, they are also used as toys for kids. It's just springs. They can be very long, but when they are not stretched, they have basically this size. So if you just stretch it, you can easily see compressional waves on that because the wave velocity will be also small. So you just push and pull at one end. You will see that the spring will be compressed in certain regions. It will be stretched in other regions. So that is what we call a longitudinal wave. On Monday, if I don't forget, I will bring it to show it to you. So how we have a longitudinal wave. Well, okay, this is how we define when we are talking about the polarization of a wave. This is basically what we will mean. There is something that is oscillating. In the case of the electromagnetic field, for example, it will be the electric field itself that is oscillating. Its average will be 0. So it will have some magnitudes. If the electric field, if this oscillating electric field, let's say at a given point, is perpendicular to the propagation of the wave, then we will say it's a transversely polarized wave. If it is in the direction of the wave propagation, then we will call it a longitudinally polarized wave. So these are the definitions, the concepts, the terminology that we will be using when we are discussing electromagnetic waves. Well, you see, let's look at that. Well, we have this slinky. A slinky, let's stretch it. So it is this one. This is our slinky. Well, it's more or less homogeneous everywhere. There is no wave over here. For example, I'm holding the left end. I can just shake this left hand up and down. Now, if I shake this left hand up and then down, I will be creating a wave. And the wave will be this, will have this shape. Now, what kind of a wave are we talking here? Well, the wave is the displacement of the mass making the slinky, the displacement from their equilibrium position. So if you just consider this point, which was initially there, or that point was initially here, now it has moved upward by some distance y. And this y is a function of x and t. X being the distance from the initial point. The velocity of this wave is in this direction. This is the velocity of the wave. Now, the displacement of the particle, if you take its scalar product with v, this is just 0. Because delta r is y in the y hat direction. This is my y direction. And v is some speed in the x hat direction. Their inner product is 0. This is what we call a transversely polarized wave. Well, since we could have shaped it up and down or left and right, there are two different transversal polarizations. Or I take the same slinky, I'm holding the left-hand side, I just push it and pull it back. In that case, what I will observe is this one. This is what I will observe. Now, this point still, originally at that point, at that position, is now over here. Now, this is the displacement of my particle, of that point. Let's say this is y. This is my delta r. Now, delta r cross v this time, this is equal to 0. They are in the same direction. So this tells me that this is a longitudinally polarized wave. For a general wave motion, here the wave is the wave of the displacement of the particles making my slinky. A general displacement, I can just decompose it into two parts. One perpendicular to the direction of the velocity of the wave, and one in the parallel to the velocity of the wave. So in general, for a general wave, it will be just a sum of a transversely polarized part plus a longitudinally polarized part. And a wave doesn't have to be either transversely polarized or longitudinally polarized. At least in this case, if you create a wave in this slinky, it can have both of them at the same time. Well, let's see. What is the direction of the momentum in this spring? Well, let me look at here. In which direction is this particle moving? It's moving forward. The wave is moving forward. At that point, the momentum flow is in the plus x direction, and the momentum is in the plus x direction. Let's look at this point. This point is now moving back. So at that point, the momentum is in the backward direction, but the flow is in the forward direction. Now let's try to apply this to our electromagnetic fields. Well, to be able to say that there is some wave in our system, we have to obtain some expression of this form. If we can show that, at least under certain circumstances, the electric field or the magnetic field satisfies an equation of this form, or let's say more generally, the Laplacian acting on f minus 1 over v squared del squared f by del t squared should be equal to 0. This is the three-dimensional generalization of our wave equation. If we can show that our fields satisfy an equation of this form, then we can say that under those circumstances, there is a wave. It is possible to create waves that move with the speed v. So that will be our aim. Does the electric field or the magnetic field satisfy an equation of this form? Now for simplicity, let's start with vacuum. Next week, we will look at what happens. Can we have electromagnetic waves in medium? But for today, let's start with vacuum. Now, what are the equations? Let's just remember our Maxwell's equations. Divergence of E is 0. We are in vacuum. So the divergence of the electric field is 0. Divergence of the B field we are in vacuum. In vacuum, there is no charge. Rho is 0. Divergence of B, well, it is 0 whether there is charge or not. Curl of E minus del B by del T. And the curl of B mu 0, J is 0, epsilon 0 del E by del T. Well, up to this coefficient, this equation and this equation, they are the same equation. Up to this coefficient. Here we have minus 1, here we have mu 0, epsilon 0. Now let's see if the electric field has some kind of a, satisfies some kind of a wave equation. Now the easiest thing to do, well, Laplacian is kind of a complicated operator. Rather than trying to see if there's some Laplacian in our equations, let's look at the second derivative of the electric field. Second derivative with respect to time. Well, the first derivative of the electric field with respect to time is the first derivative. Well, that's our last equation on the second line. Curl of B 1 over mu 0 epsilon 0, curl of B. So let me so those two equations will stay there. Well, let's look at this second derivative, del squared E by del T squared. This is equal to 1 over mu 0 epsilon 0. Position and time derivatives, I can change their order. Second derivatives, well, if you ask a mathematician, they will just list the conditions under which you can change the order of derivatives. But for us, all the functions are sufficiently smooth. So you can just change their order. So the second derivative is nothing but the curl of the first derivative of B with respect to time. I just took the time derivative of this equation. The time derivative of the left-hand side is the second derivative of the electric field. The time derivative of the curl of B is nothing but the curl of the time derivative of B. Now what I'm aiming at is to obtain an equation that contains only the electric field and no magnetic field. So I have to write that B field in terms of the electric field if I am to obtain some wave equation for the electric field. So what is the del B by del T? This is equal to 1 over mu 0 epsilon 0 curl of minus the curl of E. So that's great. That means I have a single equation that doesn't contain the B field, only the E field. So whatever E field I have, it should, in vacuum, it should always satisfy this equation. By del T squared, this is equal to minus 1 over mu 0 epsilon 0 curl of E. So do you remember what the curl of a vector field? Well, you can calculate it. You should get used to making such calculations. It will be just a couple of lines using indices. Without indices, it will be a couple of pages. But let me just write it down straight away. What is the divergence of E? Look at our Maxwell's equations. That is 0 in vacuum. So second derivative of the electric field with respect to time is equal to 1 over mu 0 epsilon 0 Laplacian of E, or the Laplacian of E is equal to mu 0 epsilon 0 del squared E by del T squared. Or, and we know that this is nothing but the wave equation, the Laplacian of something is equal to the second derivative of the same thing with a proportionality constant, and that proportionality constant is nothing but 1 over v squared. So this tells me that the speed of light, let me put the C. So there are electromagnetic waves. It is possible to create electromagnetic waves. And the speed of these electromagnetic waves has to be equal to 1 over square root of mu 0 epsilon 0. And we know the numbers mu 0 epsilon 0. We can measure them by doing experiments. And you just take two charges, measure the force between the two, measure the charges in them. That allows you to determine epsilon 0. Just take two currents, known amount of currents, measure the current, measure the force between them. That allows you to determine what mu 0 is. So none of these measurements, by the way, uses electromagnetic waves. So we have two measurements that are not related with wave phenomena. Nevertheless, the numbers we obtain from those measurements allow us to determine, not measure this time, it's determine what the wave is, what the speed of the wave is. And this wave turns out to be approximately 3 times 10 to the power 8 meters per second. Well, up to now, we didn't say anything about light, by the way. We know Maxwell's equations. Most of them, if not all, except then those time derivatives, we just determined them by studying time-independent phenomena. And those time derivatives we determined by looking at phenomena with, like, let's say, changing electric and magnetic fields. You can just take some magnets, move it around coils, and that will basically allow you to determine these formulas experimentally. And nevertheless, we predicted some kind of a wave should exist. And that kind of a wave turns out to have exactly the same speed of light. This was one of the indications that light is nothing but a kind of an electromagnetic wave.
There's another derivation in the book, E curl that equals curl of E. It drives the wave equation.
Well, you see, the book probably starts from here. For me, it's kind of, well, why take the curl of E? And how do you see that it will eventually lead to Laplacian to start with, especially if you are not experienced? For me, starting from the time derivative is more straightforward. Now you have at least two derivations. We will come to that next hour, okay? Or let's see, probably next hour. Other questions?
Hocam şimdi hani in vacuum dedik ya.
Hı hı.
del dot i sıfır dedik ama şurada del cross i'yi de yazabildik.
So,
Yani uzayın tamamını düşünmedik mi? Vakum derken. Uzayın tamamı vakum diye düşünsek hiç manyetik alan da olmaz.
yeah, okay, so what we are looking at is, I have some vacuum over here. I'm not saying that all of the space is empty. I'm just saying that there is this region of space which is empty. There is nothing in that volume. In that volume, there can be some electric field. The electric field within that volume has to be a wave. It has to satisfy the wave equation.
Yani şu önceden düşündüğümüz gibi böyle düz çizgi değil de artık dalga mı olacak?
Well, you see, is this a wave? Well, depends. You can call it a wave with zero amplitude, if you like. It satisfies the wave equation. In that sense, you can still call it a wave. Or there can be something oscillating. That is what we will call a wave. Now, what will happen there is, for example, we have this empty volume. For example, you can look at this in terms of electrostatics. Well, you put some charge over here, nearby. It will create an electric field in this volume. It will be constant in time. The charge is not moving. Just think of the electric field lines. They will be just straight lines. Now, if I move this wave, this charge up and down, what this tells me is that, okay, these electric field lines, if you want to think in terms of electric field lines, they will just act like this string. You are just shaking it up and down if you are moving this charge up and down. So that motion of the charge, up and down motion of the charge, will create fluctuations in the electric field, and those fluctuations in the electric fields have to be a wave. And so those fluctuations, as you move the charge, and the electric field is changing, at least in this volume that I'm talking about, that doesn't contain my charge, in this empty volume, they should move from one side of the volume to the other side of the volume with this speed v, these fluctuations in the electric field. So that is my claim. And indeed, when you identify the light as a kind of an electromagnetic wave, light also has the electric field inside. And you measure the speed of light. So that will be the speed at which the electric field in light propagates. And it turns out that the electric field in light propagates with this speed. No, just check the units. You see, the electric field is the same in both places. From here to there. Well, I just multiply both sides by mu 0 epsilon 0 so that the Laplacian of E has coefficient 1. By the way, this derivation was one of the great puzzles at its time. You see, we are talking about some speed. Up to that time, you know Newton's dynamics, Newton's mechanics, and you know Galilean relativity even before Newton, which states that velocity changes, and hence the speed changes from your reference frame to a reference frame. It's not the same in every reference frame. But here we drive the speed of light. In which reference frame? We didn't specify any reference frame. You see, Maxwell's equation, at least in our way of deriving them last semester, one of the arguments that we used was we wanted to get equations that are frame independent. that shouldn't change, that shouldn't give us different results in different frames. So that kind of forced us to introduce those time-dependent terms. But now we obtain a speed which Newton told us that is frame-dependent. Should be frame-dependent. So either we should give up Newton's idea about frame dependence of the velocity, at least some of the velocities, or we should try to identify some reference frame in our derivation, which without knowingly, without being aware of it, we might have made some choice of reference frame. Well, it is people first try to, the second way they didn't, I mean, Newton's law were verified for many years. So they didn't want to give up on Newton's laws or Newton's dynamics. So they looked at the reference frame in which the Maxwell's equations are correct, or the reference frame in which the speed is correct. But if there's such a reference frame, of course, the prediction is in a different reference frame, the speed should change. You should measure different speeds for the speed of light in various different reference frames. And that was the motivation of the Michelson-Morley experiment. They said that the reasoning was that, okay, there is some reference frame in which this is the speed of the electromagnetic waves. And they said that, okay, let's call that reference frame the ether, the reference frame in which the ether is at rest. Another problem with this wave is all the wave phenomena we know, like the wave on a string, they are the fluctuations of a medium. So here is the string that is vibrating. In the sound waves, it's the atmosphere that is vibrating. In ocean waves, water waves, it's the liquids that is vibrating. So here we have a wave. So what is vibrating? Now, there were various ideas, like one of them was the ether idea. So the universe is filled with this substance called ether. And its oscillation gives us these electromagnetic waves. But that also answered one question. This is the speed of the electromagnetic wave in the reference frame in which the ether is at rest. Okay, that is a nice hypothesis. That is, it answers our question, but where is the proof? So what Michelson-Morley did was, Earth is moving in some direction. So if you pick up two perpendicular directions, most probably one of them will be close to the direction of the motion of the Earth in ether, and the other direction will be almost perpendicular to the direction of the ether. So speed of light in these two directions should be different. And that difference they could measure by doing an interference experiment. And they measured no difference. Now the only possibility is that these two directions, they are just 45 degrees with the direction of motion of the ether. But, well, you can just change the orientation. At least with the new experiment, they shouldn't be at 45 degrees, at least not both of them. So that kind of proved that the speed of light doesn't change. Of course, still people didn't want to give up the idea of ether. They proposed that, okay, so there is ether, but the ether is dragged with the Earth, so ether is also not at rest, it is moving, etc. So they all try to come up with keep with the idea of ether and make it consistent with experimental observations. But the easiest explanation came with Einstein's special theory of relativity, which said that this is the speed of light in every reference frame. And he had his special theory of relativity, etc. And his conclusion was, even if there is ether, there's no way you can measure it. So from a philosophical perspective, we said that if we cannot measure it at all, then it doesn't exist. Okay, so another thing, okay, there is electric field does satisfy a wave. Well, look at our equations. If electric field is not zero, the B field cannot be zero. It's a wave. If the electric field is changing in time, so there is an accompanying B field. I will not go over the derivation, but if you just repeat the same thing, you start with the second time derivative of the B field, and you will see that the B field also satisfies exactly the same equation. So there is the electric field satisfies a wave equation. The magnetic field satisfies a wave equation. So we do have solutions of both the electric field and magnetic field that are waves. First thing, what are their properties? So meaning that we had already discussed the general properties of waves. What are the possible wavelength frequencies? Their polarizations, are they transversely polarized, longitudinally polarized? And how can we create them? Eventually, that's what we will study. The first thing we will discuss is, well, what are their properties? And then after that, we will discuss how we can create them. And then we can do experiments, and we will come to your question. Why do we, if light is an electromagnetic wave, is it the only form of electromagnetic wave? Are there other forms of electromagnetic waves that are not visible to our eyes? What causes some light, some electromagnetic waves to be visible, some of them to be invisible to us, etc.
Hocam bir şey sorabilir miyim? Hani biz dedik ya şimdi bu hız işte tüm referans frame'de sabit diye. Ama bu gene bu hani hangi medium dalgalanıyor falan ona bir açıklama getiriyor mu?
Well, the idea is that the electric wave propagates in the B field. And the B field kind of propagates in the E field. So what's basically happening is, let's say you create some electric field in a region, and then you try to change that electric field. You have this charge, you move it up and down. You are changing the electric field. But that change in the electric field is creating the B field. Now, even if you stop the cause that is changing the electric field, now the B field is changing, so it's creating a changing electric field. Then you have a changing electric field which creates a changing B field. So basically, that it creates what we call a self-sustaining system. It doesn't need anything else. Because once the electric field, if the electric field tries to go to zero, you are creating a large B field. But once the change in the electric field disappears, then the B field, well, you would expect it to disappear, but as it's disappearing, it creates the E field, etc. So the E and the B fields they create each other. They sustain each other. But this also tells us that you cannot talk about electromagnetic waves that are purely electric, or you cannot talk about electromagnetic waves that are purely magnetic, because they are creating each other. That is what we said. I mean, any change, well, you see, the wave is a perturbance. It's a change in certain properties of our system. So since the E field satisfies the wave equation, it tells us that any change in the electric field propagates with the speed of light. So if I take this, you imagine some charge over here. If you displace it vertically upward, let's say, that is changing the electric field. But that change will affect some other point over there after a time that is equal to the distance divided by the speed of light. That point over there will not know that this charge has moved upward before that time. Because to determine the position of this charge, what it does is it measures the electric field. And before that time, the electric field at that point does not change.
Hocam ölçüm yaptığı zaman buradaki parçacık çoktan aşağı inmiş de olabilir.
True.
Peki parçacığın pozisyonunu nasıl ölçecek oradaki insan?
It cannot. It can only say what the position of that particle is before. And if it knows how the particle moves, let's say it makes many measurements and it knows that the particle is moving at constant velocity, and it can say that, okay, that particle is such a distance away from me, so when I see its position, let's say 1 second before. So if I want to calculate the position now, I should make the correction. It's just like if you look at the stars. You know their position, their brightness, etc. years before now. At this moment, in this reference frame, let's say, because Einstein also said that if you want to talk about the time, you have to talk about you have to first pick out a reference frame. In our reference frame, in the reference frame fixed on me, let's say, the stars at this time, they are probably at a different point. Some of them might have even disappeared. I don't know, we cannot know it. If we know how the stars change their position, their properties, etc., we can only make predictions about what their properties are by just, for example, the Andromeda galaxy is, I think, how many? No, the closest star is 4 light years away from me. So what I see is the star that it was 4 years ago. If I want to know what the star is now, I have to know its properties. I have to make a prediction for the future of the star. I will see its current position 4 years from now. Now let's see. The electric field satisfies this equation. And this constant over here, it doesn't depend on what creates the electric field or what creates the wave. So, you see, whatever the electric field is, whatever is creating the electric field or the magnetic field, the created electric and magnetic fields, they should satisfy these two equations. This constant appearing over here is independent of what creates the B field or what creates the electric field. We didn't make any assumption on the origin of this B field and the E field. What we know is that whatever the origin of our electric and the magnetic fields are, they should satisfy our Maxwell's equation in vacuum, or I consider this finite volume, which is empty. In that finite volume, my electric and magnetic fields in that volume should satisfy those equations independent of whatever creates them. And in that volume, these should be the equations they satisfy independent of whatever is creating them. And these two equations are telling me that this should be the speed of propagation of changes in the electric and magnetic field. Again, what will be the changes? I don't know. I mean, those are what determines what creates the electric and magnetic field. Once we know what creates the electric and magnetic field, then we can say that how it is changing at a given point. But we already know that that change is moving with that speed, c. Okay, so let's give a 10-minute break and we will continue after the break.